Introduction to Computing and Quantum Computing. When you hear the word computer, you probably think of your phone, your laptop, or maybe even a gaming console. But computing isn't really about devices. It's about decision-making. At its core, computing is how humans use machines to process information, follow rules, and solve problems. Today, we're exploring not just how computing works, but why scientists are building new kinds of computers to handle the world's biggest challenges. What is computing? Computing is the process of taking input, applying rules, and producing an output. You already use computing every day. A calculator takes numbers and gives you an answer. A search engine takes your question and returns results. Navigation apps calculate the fastest route in real time. Behind all of this are billions of tiny electrical signals making simple yes or no decisions. These decisions form the foundation of everything digital. Even though modern technology feels complex, it's all built on simple logic repeated at incredible speed. Classical computing. Traditional computers are called classical computers. They store and process information using bits. A bit can only be one of two states, 0 off or 1 on. Every photo, video, message, and app is broken down into long strings of these zeros and ones. Classical computers process these bits step by step at incredible speeds. They are extremely powerful, but they have limits. As problems grow more complex, the number of possible solutions grows exponentially. For example, imagine solving a giant maze. A classical computer tries paths one at a time, checking every possible route until it finds the exit. This works, but can become very slow for large or complicated problems. Still, classical computing isn't outdated. Researchers are using quantum-inspired ideas to improve classical systems, from encryption to optimization, showing computing continues to evolve. Why we need new kinds of computing. Some problems are too complex for classical computers to solve efficiently. For example, modeling molecules to create medicines, optimizing systems like supply chains or traffic networks, securing or potentially breaking modern encryption. These problems involve massive numbers of possibilities. Trying each one individually can take longer than the age of the universe. That's why researchers, including companies like IBM, Google, and Microsoft, are exploring a new approach: quantum computing. What is quantum computing? Quantum computing uses the laws of quantum physics to process information in a different way. Instead of bits, it uses qubits. Unlike a regular bit, a qubit can exist as 0, 1, or both at the same time, a concept called superposition. A helpful analogy: a classical bit is like a coin lying flat, heads or tails. A qubit is like a spinning coin, representing both possibilities at once. Quantum systems also use entanglement. Qubits are linked, so changing one affects another. Interference helps amplify correct answers and cancel out wrong ones. Together, these properties allow quantum computers to explore many possible solutions simultaneously instead of one at a time. So going back to the maze analogy, a classical computer searches every path. A quantum computer behaves like it has a bird's eye view, narrowing down the correct path without checking every dead end. Real-world impact and challenges. Quantum computing has the potential to transform industries, discovering new drugs and materials, improving artificial intelligence, solving complex optimization problems, rethinking cybersecurity through algorithms like Shor's. But there's a catch. Quantum systems are extremely delicate. They require temperatures close to absolute zero, careful isolation from the environment, advanced error correction. Because of this, large-scale quantum computers are still in development. Experts estimate it may take years, even decades, before reaching full potential. Quantum computing doesn't replace classical computing. It extends it. In fact, you can think of quantum computing as a broader system, where classical computing is just one part of the bigger picture. As our questions become more complex, our tools must evolve too. And understanding computing, from bits to qubits, is the first step toward understanding the future of technology.